Time travel is a concept that has long captivated the minds of scientists and science fiction enthusiasts alike. Although no one has yet managed to travel through time, at least to our knowledge, the question of whether or not such a feat would be theoretically possible continues to fascinate scientists. As movies such as The Terminator, Donnie Darko, Back to the Future and many others show, moving around in time creates a lot of problems for the fundamental rules of the universe. For instance, if you go back in time and stop your parents from meeting, how can you possibly exist in order to go back in time in the first place? This is known as the grandfather paradox, and it has been a long-standing problem for scientists who have been trying to figure out a way to make time travel viable without the paradoxes. A few years ago, however, physics student Germain Tobar, from the University of Queensland in Australia, worked out a solution. He found a way to square the numbers and make time travel viable without the paradoxes. He based his solution on two theories of physics: the theory of classical dynamics and Einstein's theory of general relativity. Classical dynamics says if you know the state of a system at a particular time, this can tell us the entire history of the system, said Tobar. However, Einstein's theory of general relativity predicts the existence of time loops or time travel, where an event can be both in the past and future of itself, theoretically turning the study of dynamics on its head. Tobar's work suggested that spacetime can potentially adapt itself to avoid paradoxes. To use a topical example, imagine a time traveler journeying into the past to stop a disease from spreading. If the mission was successful, the time traveler would have no disease to go back in time to defeat. In Tobar's model, the disease would still escape some other way, through a different route or by a different method, removing the paradox. Whatever the time traveler did, the disease wouldn't be stopped. Tobar's work isn't easy for non-mathematicians to dig into, but it looks at the influence of deterministic processes, without any randomness, on an arbitrary number of regions in the spacetime continuum, and demonstrates how both closed time-like curves, as predicted by Einstein, can fit in with the rules of free will and classical physics. The math checks out, and the results are the stuff of science fiction, said physicist Fabio Costa from the University of Queensland, who supervised the research. The research smoothed out the problem with another hypothesis, that time travel is possible but that time travelers would be restricted in what they did, to stop them creating a paradox. In this model, time travelers have the freedom to do whatever they want, but paradoxes are not possible. While the numbers might work out, actually bending space and time to get into the past remains elusive. The time machines that scientists have devised so far are so high concept that they currently only exist as calculations on a page. We might get there one day. Stephen Hawking certainly thought it was possible, and if we do, then this new research suggests we would be free to do whatever we wanted to the world in the past. It would readjust itself accordingly. Try as you might to create a paradox, the events will always adjust themselves, to avoid any inconsistency, said Costa. The range of mathematical processes we discovered show that time travel with free will is logically possible in our universe without any paradox. Germain Tobar's research is an important step forward in understanding the possibilities and limitations of time travel, and although the idea of actually building a time machine may still be far-fetched, the research suggests that it is theoretically possible. It is important to note that the research is still in its early stages and more research is needed to fully understand the implications of Tobar's findings. However, it is certainly an exciting area of study that has the potential to reveal new insights into the nature of time and space.